All right, today we're going to add to our discussion of linear regression. We talked about how to find the equation of the linear regression and how to find R and what it stood for. I wanted to talk about first just these formulas. There was a time when you couldn't just type your data into a calculator and get all these nice values spit out for you. These formulas you will find on your pinky sheets, and you will find them on the AP test. You don't usually have to use them to calculate these values, but sometimes they'll ask a question in a certain way. They'll give you the slope and give you the correlation and ask you for the standard deviation of one of your variables. So you just need to be aware of these equations and know where they are on your formula sheets. The first one is for the correlation. So you can kind of see what all those parts are. And write these formulas down, by the way, just to familiarize yourself with them. You can see how you would find the correlation. You would take each value, subtract the mean, divide by the standard deviation. This is just the x values. Do the same for the y, multiply those together one at a time, add them up, divide by n-1, that sort of thing. We will probably never use that one. The other one, this is the equation for linear regression, a plus bx. And we did this on our calculators by going stat calc 8. I wanted to point out a couple things. First of all, this little hat on top of the y, it's pronounced y hat. That is to emphasize the fact that this is a predicted y value that we're calculating. Your line is made up from several dots. Those dots are the xy points. So those y's are actual y values that happened. This y is a predicted y, and this hat indicates that. So b is the slope, and if you had to calculate this by hand, you would find the correlation, which you found above, multiply that by the two separate standard deviations. Since we're dealing with paired data, there are two of everything. That would give you the slope, and to get the intercept, you would take that value, b, multiply it by the average x, take the average y, and subtract that total. So you can see how these formulas would work if you were doing this 50 years ago. But at the same time, there might be questions that make you use these formulas from time to time. All right, so next on the agenda for the day, influential points. I want to go back to the same data that we talked about in our calculator when we talked about linreg. The points that I have added, or that I have, and with a line going through, those are the same ones from the last video. I've gone into stat and edit, and I've added another point. All right, I've added 45, 110. An influential point is it's easy to confuse with an outlier. An influential point is a point that is far out in the x direction. An outlier is different from the pattern in the y direction, so far away from the line. But an influential point is far out in the x direction. I'm going to actually move this a little closer to the line. I don't want it to be that crazy of a point, so I'm going to make it 45 and 175, and we'll see how that looks. All right, so actually that's not going to be influential enough. I'm going to make it 45 and 150. Okay, so this point that I've added is influential. It's sort of like, again, like with the physics. If you are at the end with torques, if you're pushing on the outside edge of a door, it's easier to turn than if you push close to the hinges, or a teeter-totter. You can balance out a really heavy person by moving further away from the middle than they are on a teeter-totter. So I haven't recalculated my linear regression yet. I'm going to go back and do that. You'll notice here in the middle where I can still see in my Y menu the slope and intercept. The slope and intercept are 287 and negative 2.365. Let's see how that changes when I put in this influential point. And it's called that because it should influence what's going on. Okay, so you can see now my slope is negative 1.73 and my intercept is 244. And you can still see over next to that my old menu hasn't been reset because I didn't put this equation into Y1. It went down, or it went from 287 down to 244, and my slope went from negative 2.36 to negative 1.73. And actually, let me add that to my graph, and we'll see how it changes. Or if you put Y1 after that, it's going to put it into its place. And then if I go to my graph, zoom 9, remember zoom 9, our line has changed quite a bit. It was like this a minute ago, and that one point has really pulled a lot. That's why it's called influential. And only points that are on the edges, the left and right edges, can be that influential. If you had a point, just hypothetically here, if you had a point, get rid of that ink. Let me get rid of my influential point and talk about an outlier. An outlier can change your linear regression. It'll change the slope and the intercept, but it's not going to change it a lot. On my picture, if I zoom 9 again to get back to where I was, if I had an outlier that was, right here, that might make my line shift up a little bit. But that's not going to really tilt my line on a whole new angle the way an influential point was. So an outlier is far away, an influential point is on the edges, and it can really tilt your line a lot. Okay, so let's call that our discussion on influential points. And really, I just wanted to show you that calculator stuff. So as far as notes go, these points will be on the far left or right. And they can really change the equation that you get. It'll really change your A and your B values. That they are influential, more than an outlier could be. All right, next topic. We've got several small topics today. Residuals and the residual plot. The definition of residual is a residual is equal to the actual y minus the predicted y. And that's very easy to mix up because you're going to have two values, and how do you know it's not predicted minus actual? I remember because this is AP stats, so it's actual minus predicted. So what that means is, if you go back to your graph, for each one of these spots on my graph, each one of these dots, there's an actual y value. Let's get this point. This point right here, for instance, is 73,127. The actual y value is 127. The predicted y value is right here on the line. If I plug 73 into my line, I'm going to get this. .59. So the residual is the difference, actual minus predicted. The actual, can't even remember, I think the actual is 127, my predicted is 117. So this point has a residual of about 10, and that's this distance right here. All right, so that's the definition of residual. More importantly, for this particular class, is the idea of a residual plot. A residual plot, it's not one of my favorite graphs because the information we're going to gather from the residual plot, we can pretty much gather from the original scatter plot. A residual plot, instead of just plotting the values, the y values along with the x's, it's going to plot each one's residual. So back to our calculator. Whenever you do linear regression, after you've calculated linreg, go back to second stat, which is the list menu. And if you go down, whenever you do linreg, a list is automatically created for you called resid. And that's the residuals for each point. All right, it goes ahead and calculates every y value, the difference between the actual dot and the value that the line would predict for it. So to make a residual plot, here's what we're going to do. Go back into your lists. I'm going to skip over to list 3, go up and highlight L3, and I'm going to basically program list 3 to be the residuals. So with L3 highlighted, go back to second stat, choose resid, and you're telling L3, I want you to be the residuals. Now, if you redo linreg again for a different problem, you're going to have a new set of residuals. So this set is always up to date as soon as you hit linreg. Okay, so there are the residuals for each value. That top one is the one I just calculated. I had it about 10, it's 9.4. Now, to make a residual plot, let's go to stat plot, plot 1, and I want to do a scatter plot, but instead of list 1 versus list 2, I'm going to do list 1 versus list 3. So my x values are the same, but instead of plotting the actuals, I'm going to plot the residuals. Now, if I just go to graph, I'm probably not going to get a good picture. No, I get this question all the time. Why does my calculator say dim mismatch? And almost always, my answer will be, just a moment, almost always my answer will be go to zoom 9. In this case, my residuals had the other point, the influential point still in there, so I had to go back and take that point out. But here's the residual plot. If you remember what our graph looked like, it was a nice even scatter of points on both sides of the line. All this basically does is it sort of tilts your scatter plot, and it's graphed on a different scale. You know, the old scale would have been up in the 100s for the steps, and these numbers are scattered around 0 from, you know, +10 to -10 to, I can hit trace and look at a few of them. There's that first point. And it doesn't really tell me much that I couldn't tell from just a scatter plot, which is why it's not my favorite graph. But that's how you make it. And it is an important graph because the AP people say it's important. So until they don't, it's going to be important. So why are we going to make this plot? Well, it tells us, is a linear model good? Is it appropriate to summarize this data with a straight line pattern? What we want to see is a random pattern all over the place. A random pattern means linear is good. If you see other things going on in your residual plot, like, then that means linear is not good, and we need a different kind of model, and linear regression is not the one we're going to want to use. If you see things like this where it's getting more spread out as time goes on, or less spread out, then it's probably not going to be good. But all these things, again, could be seen in the original plot anyway. All it does is rescale your same dots and kind of tilt them to make what used to be the regression line now the x-axis. So that's a plot. If I give you a question that says, is linear an appropriate model, you want to make a plot, a residual plot, and look for just randomness. This is no good, no good. What we want to see, if linear is appropriate, is just kind of, and by the way, your x-axis will be there because you have the same amount of, if it's appropriate, you'll have about the same amount of dots below as you do above the axis. So this is 0, and that axis would be on these as well. But any curvature or weird pattern you could have seen anyway. So that's residual plot. One more thing. Coefficient of determination, R-squared. This is the number that pops up when you're calculating your correlation in linreg. Okay, I'm getting close to my time cutoff here, so I went ahead and paused. You can pause here and copy this down. Coefficient of determination, when you get R and R squared on your calculator, this is what R squared means. It's the percentage of the variation in Y that is explained by the least squares regression of Y on X. You need to remember that wording. That wording is going to pop up on test questions, on your AP test. That is what R squared means. Loosely speaking, it's the percentage of Y that's based on X. When we walked around the hallway and we did our linear regression, when I get R squared is about 62%. Basically, a very loose, not appropriate way to think of it, but sort of a kind of appropriate way to think of it is 62% of our steps was based on our height. The other 38% was based on other factors, like what path we chose and how big our steps are and how long our legs are and that sort of stuff. We'll talk more about R squared. I need to keep this under 15, but remember that wording. Make sure you have that wording written down because it's going to pop up and you're going to need to recognize that as R squared. All right, Young out.